Welcome to the deep dive. Today we're getting into something pretty fundamental if you're looking at senior software engineering roles, especially with big systems.
Yeah, we're talking distributed systems consistency.
Exactly. And specifically, we want to focus on leaderless replication. It's a really key architecture for building systems that stay up and running.
It really is. Understanding how these leaderless systems keep data consistent, especially when servers inevitably fail, that's a big deal. It shows you really get how to build reliable stuff.
Leaderless replication. I mean, the name kind of gives it away, doesn't it?
Yeah.
It suggests it's different from the usual leader-follower setup.
It is. The core difference is, well, in leader-based systems, you have one boss, the leader, handling all the writes.
Right.
But with leaderless, any replica can take a write request straight from a client. There's no single node calling all the shots on the order.
Okay, so it's much more decentralized than for writes. Why did this approach become popular? Sounds potentially complicated.
Well, it really gained traction with systems needing super high availability, massive scale. Services that just can't go down even if some servers are out and need to handle tons of writes.
Okay.
The ideas behind it really shaped a lot of well-known data stores famous for being robust.
Interesting. So if there's no leaders sorting things out, how does the data actually get copied around to multiple replicas?
It varies a bit. Sometimes the client application itself just pushes the write out to several replicas.
Okay.
Other times you might have like an intermediary node, a coordinator that takes the write and then forwards it. But the key thing is, unlike a leader system, neither the client nor that coordinator enforces a strict global order for all writes across all replicas. Each replica just handles the writes it gets.
Okay, I think I get the basic idea. But let's talk reality. Servers crash, networks get flaky. What happens in a leaderless system when a node just drops out during a write?
Yeah, good question. And this is where that resilience really comes into play. Let's say you've got your data on 3 replicas, n equals 3. And one of those servers goes down, maybe for maintenance, or just fails. A write can actually still succeed.
How?
Because you can configure the system to say, look, I only need acknowledgements from, say, 2 out of the 3 replicas for this write to count. So even if the third one is down and doesn't respond, if the other 2 say, got it, the write is considered successful. The system kind of makes a note that the third one missed out.
So it doesn't need unanimous agreement. That seems vital for keeping things available.
Exactly. You set a threshold, a quorum, rather than needing everyone. It lets the system tolerate some failures without just stopping writes completely. But as you might guess, this can cause issues later.
Right, because if that node that was down comes back up, it missed the write. So if someone tries to read from it...
They could get old data, exactly.
Yeah.
A stale read.
Okay.
If a client happens to connect to that node right after it comes back, before it's caught up, it might serve outdated information. That's the risk if you just read from one replica, especially after failures.
Okay, so we've got better write availability when nodes fail, but now we might read stale data. How do these systems fix that? How do they try and keep reads consistent?
Well, they have mechanisms to spot and fix these things. One really important one is called read repair.
Read repair?
Yeah. The idea is when a client reads data, it doesn't just ask one replica. It asks several, maybe 2 or 3 in parallel. And each replica sends back the data it has, usually with like a version number or a timestamp.
And if the versions are different?
Bingo. That's the repair part. The client sees the different versions, figures out which one is newest based on the version number. And if it finds a replica with an older version, the client itself actually writes the newer version back to that stale replica.
Oh, that's clever. So the act of reading actually helps heal the system.
Exactly. It uses a common operation, reading, to fix inconsistencies. It's often more efficient than relying only on some background cleanup process for everything.
Can you give a quick example? Like, how would that play out?
Sure. Imagine you're checking the count on your photo. It's stored on 3 replicas.
Okay.
You hit refresh. The system asks all 3, 2, 15 likes version 3, but 1, maybe I had a network blip earlier, says 14 likes version 2.
Right.
The client sees version 3 is newer, so it shows you 15 likes, and it sends a quick write back to that third replica saying, hey, update this to 15, version 3, boom, repaired. Works great for stuff that gets read a lot.
That makes total sense for frequently accessed data. But what about data that just sits there, hardly ever read? Read repair won't help much there, will it?
Good point. No, it won't. For that less read data, there's usually another mechanism, an anti-entropy process.
Anti-entropy. Sounds fancy.
Yeah. It's basically a background process. It runs periodically, maybe overnight, maybe continuously, but slowly. And its job is just to compare data between replicas.
Like a reconciliation.
Pretty much. It looks for differences, missing data, old versions, and if it finds any discrepancies, it copies the correct data across to bring the lagging replicas up to speed.
So it's aiming for eventual consistency behind the scenes.
Exactly. But it's different from, say, the strict ordered log you get in leader-based replication. Anti-entropy is more about just comparing snapshots and syncing them up.
So there might be a delay.
There can be, yeah. Depending on how often it runs, it might take a while for rarely accessed data to become consistent everywhere just through anti-entropy alone. And interestingly, not all systems even have both. Some might lean more on read repair, some more on anti-entropy. Some might even skip one, which affects durability, especially for data you don't read often.
Wow, okay. Lots of trade-offs. Now, you mentioned needing a certain number of acknowledgments for writes and querying a certain number for reads. These numbers sound critical.
They absolutely are. This brings us to quorums, defined by three numbers: N, W, TR.
Okay, N, W, R. Break those down for us.
So N is just the total number of replicas holding the data. Simple enough.
Okay.
W is the write quorum. That's the minimum number of replicas that must confirm a write for it to be considered successful.
Okay, W for write.
And R is the read quorum. The minimum number of replicas you need to contact and get a response from during a read.
R for read. Okay, N, W, R. How do they work together?
So think of it like voting. A write needs W votes to pass. A read needs to consult R voters.
Okay.
Let's use our example of N equals 3 replicas again. You could set W equals 2 and R equals 2.
So 2 need to confirm a write, and you need to ask 2 for a read.
Exactly. A write only succeeds if at least 2 replicas say OK. And a read operation has to successfully get data back from at least 2 replicas.
Now, I feel like there's a math rule here that's really important for consistency. Something about adding W and R.
Yes, you've got it. The crucial condition is W plus R is greater than N.
W plus R is greater than N. Why is that the magic formula?
Because if that condition holds, W plus R is greater than N, it mathematically guarantees that your read quorum R and your write quorum W always overlap on at least one replica.
Overlap?
Meaning there's always at least one replica that was part of the most recent successful write group, W, that is also part of the group you're currently reading from, R.
Ah, okay. Can you maybe walk through that with slightly bigger numbers?
Sure. Let's say N equals 5 replicas, and we choose W equals 3 and R equals 3.
Okay, W is 3, R is 3. So W plus R is 6, which is greater than N, which is 5. Condition met.
Perfect. Now imagine a write comes in. It succeeds because replicas A, D, and C acknowledged it. That's our W quorum of 3. Maybe D and E were slower down.
Got it. A, B, C saw the latest write.
Now later, someone does a read. The system needs to contact R equals 3 replicas. Let's say, worst case, it picks C, D, and E.
Okay, C, D, and E for the read quorum.
C, the overlap. Replica C is in both sets. It was part of the successful write quorum, A, B, C, and it's part of the read quorum, C, D, E.
Ah, so because C saw the latest write, the read operation is guaranteed to see that latest value from C, even if D and E have older data.
Precisely. That overlap, forced by W plus R, is greater than N. Ensures you always read at least one copy that's up to date with the latest successful write. That's how you get strong consistency guarantees without a leader. It's pretty elegant.
That is elegant, and it makes sense why those W and R values are like tuning knobs.
Absolutely. You can tune them for different needs, like maybe you have a super read-heavy workload and low read latency is paramount.
Yeah.
You could set W equals N, so all replicas must confirm a write, and R equals 1, so reads only need to hit one replica. Reads are super fast.
But the catch is?
The catch is availability. If W equals N, then if even one replica is down, no writes can succeed at all, because you can't get acknowledgments from all N replicas.
Ouch. Okay, so that's a trade-off. And presumably, setting W and R lower gives you more fault tolerance.
Exactly. If W is less than N, writes can succeed even if some nodes are down. If R is less than N, reads can succeed even if some nodes are down. You gain availability.
But you need to be careful that W plus R is still greater than N if you want that strong consistency guarantee we talked about.
That's the key balancing act. Tuning W and R is all about finding the sweet spot between consistency, availability, and performance for your specific application.
This has been super helpful. We've really unpacked leaderless replication, the basics, how it handles nodes going down, the cleverness of read repair, the backup of anti-entropy, and critically, these quorum concepts with N, W, and R, and especially that W plus R is greater than N rule for consistency.
Yeah, these are definitely core concepts. If you're designing or operating big distributed systems, you really need to grasp these ideas. And for interviews, absolutely.
For sure, being able to explain this stuff clearly, talk about the trade-offs, that's what distinguishes senior candidates, right?
Without a doubt. It
Yeah.
shows you understand the real-world complexities.
Okay, so for everyone listening, especially if you're prepping for those senior interviews or dealing with system design, really internalize these concepts and maybe here's something to chew on. Imagine you have a system where you desperately need both high availability and really low read latency. How would you even start thinking about picking W Aurora? What factors push you one way or the other? It's not always easy. Definitely worth thinking about those trade-offs. Thanks for joining us for this deep dive.